Tell me, what do you remember? What's the definition of Gibbs free energy? Anybody? Anybody? B, okay. B. Okay.
It's funny when you ask like what it means.
The energy, yeah. Available to do work. Thank you. Available to do work. Okay, so we're relating it back to work. Work is is literally measured in joules, just like Gibbs free energy is measured in. And work can usually mean like expand. For chemistry, it's expanding, like pushing like a system outward on our surroundings. But like in physics, it's more moving of distances. So for those of you in physics, you'll see work is a different thing. Okay, so Gibbs free energy is the energy available to do work, which is measured in joules, right? Then we also know. Oh, I got you here. What? And then delta G, don't forget delta G is the symbol for Gibbs, so that's our equivalence there. Gibbs free energy is work, W. All right, so, well, no, I'm going to show you this one. This is a known that I'm going to tell you. You probably know a little bit about it, but I'm going to go ahead and tell you now. There's the cell energy, the E cell, the standard cell potential, and we have work. Well, the standard cell potential is the work that we are doing. It is the energy that's being put out of the battery, and we use it. If we can extract that energy, with a little external wire, we can capture that energy and we can do something with it. We can do work with it. So they're intertwined. But you'll notice that the cell potential is E cell, right? It's measured in volts, and the work is measured in joules. So we know that there's going to be some sort of conversion between the two because they're directly related. The more energy we can create from the battery, the more work we can do. But we got to kind of convert between the two. So, but we do have to remember our system versus surrounding the big thing here. So the cell itself, anytime we're talking about a galvanic cell, we say it has a positive E cell. Anytime we're talking about work done, it's usually work done on the surroundings. So that's when we have a negative W. A negative W means the system has lost that work, has lost that energy. So that's going back a little bit to thermochemistry and thermodynamics. So positive E cell equals a negative work. But, we still have to deal with this whole unit issue. This one's in volts and this one's in joules. What was a volt yesterday? You wrote down last part of your notes. 1 joule per coulomb. Okay, coulomb is just big C. Okay, coulomb is just a unit of charge of electrons, because we all know electrons have charges. So that's what our next part is here, okay? Let me go ahead and tell you this first. The reason, and I just explained this part right here, but galvanic cell, and then current flows out of the cell, so that's what I'm talking about. Flowing out of the cell means the system is losing that energy, so that's why it's got the negative perspective there. Okay, we just said voltage was joules per coulomb, right? So when we're talking about E cell, which is measured in volts, or voltage or volts, that is, and I just noted the units here in red. So what we're saying is E cell is negative work per Q. Negative work, which is joules, and then Q, which is a measure of charge. It's not heat in this one, okay? So Q with electrochemistry is charge. Q with thermodynamics and thermochem is heat, right? So this Q is not heat, okay? And so I just wanted to show you this connection, joules and work, and then coulombs and charge. All right, good so far? All right, so we're kind of going to start breaking down how can we convert between E cell and charge, or E cell and work. We usually are not too concerned about work, but we are concerned about Gibbs free energy, which is what work is related to or equal to. So that's what we're kind of eventually getting down to. All right, so what I did was I took my E cell here equals to negative W over Q, and I rearranged it so I could get just negative W by itself. So if you're mathematically minded, this is all you, all over the place right here, okay? So I just multiply by Q. So E cell times the charge is equal to the negative work, or the work lost by the system. All right, so what I have here is volts times coulombs is equal to joule. That's what the work is, which is essentially this rearranged. It's the same story. I just have rearranged some units here. All right, so the only reason I'm getting this is because I need to eventually get to using charge and what else that charge can be represented by. Because what I said earlier was charge is a unit of, coulombs is the charge of an electron, right? So we know we're dealing with redox, we know we're dealing with electrons, but some of these cells are going to deliver more electrons than others. So more electrons delivered would probably yield more charge or more coulombs delivered. And if you have more charge or more coulombs, you possibly are going to have more volts. So it depends. So we got to look at this here. So what actually is this Q thing? Q is the charge of a certain number of moles of electrons. So if you have more electrons, you're going to have more charge. Does that logically make sense? Okay, cool. Now we can quantify that charge. Quantify it by looking at how many electrons we have and the specified constant as to, X number of coulombs occurs per mole of electrons. That's called the Faraday constant. You saw this last night on the simulation part? Yeah? Okay. So Q, which is charge, is equal to N, which N has always been moles, right? Okay, in this case we're talking about moles of electrons, times the charge that each moles of electrons carry, which is the Faraday constant. So charge is equal to number of, moles of electrons transferred throughout like a redox reaction times the Faraday constant, which is 96,485 coulombs per mole of electrons. Huge number. If we're rounding, I always just assume that's about 100,000. I can multiply by 100,000 a lot better than I can multiply by 96,485. So usually rounding, sometimes they'll say like 96,500 if you're good with that, but you can always round, adjust your rounding. So what was the unit of Q again? Coulombs, right? So they're so cool. So Q, which is coulombs, is equal to moles of electrons, which is our N, times Faraday constant, 96,485 coulombs per moles of electrons. And so you can see mathematically, or stoichiometrically, units, dimensional analysis, whatever you want to call it. There you go, moles and moles cancel, so that does get you your coulombs that you're looking for. Okay, so this is going to be, we're going to be more interested in this tomorrow, because we're going to actually calculate how much charge is delivered, how many electrons are used, how long does it take to deliver this charge, stuff like that. Okay. And, okay, sorry, I have to show you this too. So what I did here was, previously we had stated E cell is equal to joules over coulombs, right? Volts is equal to joules over coulombs. So what I did here was I took this equation, because we rearranged it here, and I said, oh, okay, well, if Q is equal to NF, well, then I can just plug in NF right here. Okay, so I just did a simple substitution. I'm trying to show you how we eventually get to another equation. So after doing a simple substitution, plugging in the N and F, still equal to negative W. I don't really like that whole negative W thing, so I'm going to rearrange further. So all I did was I said, okay, I need to get work by itself, because the very, very, very beginning, we said what was equal to work. Gibbs free energy. So delta G is equal to W. Okay, we're not dealing with like perspectives on that one, because they are the same perspective. So not one of them is not positive, one of them is not negative. Delta G is equal to a positive W. Okay, so essentially I'm getting a positive W here, which I can then say is equal to delta G. Yeah? Okay, so that's my final call down here. So all I did was took my negative W, so then I have negative here. So negative E cell times NF is equal to W. Then I was like, okay, well, W is work, which is Gibbs free energy. So Gibbs free energy is equal to negative NFE. NFE. That's how I've always remembered it. So I have it written, as E cell first, but I just rearranged it so it looks like what you get on your reference table. So this is a good equation that can allow for you to actually do something you've never been able to do before. You can do an experiment, you can get some data, and you can plug into an equation and actually get Gibbs free energy. We've never been able to experimentally be able to determine Gibbs. We've always had to go, okay, well, what's the delta H? Look at a table, do H of products minus H of reactants, and what's the delta S? Look in the back of the book, look at all the entropies. We've never been able to gather data from an experiment and do it. So what you should see here is that you can be given experimental data on the test, or the FRQs for AP exam, and you can actually experimentally determine Gibbs. Or you can do it from tables with the thermodynamic constants and stuff like that, okay? So this one's relating Gibbs free energy to E cell. And usually I would have, my standards written there like that. This can also be non-standard conditions. Delta G is equal to negative NFE. Non-standard, so no little knots there. We're going to talk about non-standard conditions in just a second. All right, cool. So, you don't have to memorize how to connect the dots, but I wanted this to make sense to you, not be like, hey guys, memorize this formula. Okay, so we can prove how to get places. And then I have to make sure you guys know this. This N right here is total moles of electrons in the BCE. So you have to have your redox formula all the way kind of panned out and get like, oh, total moles of electrons, or 4 moles of electrons transferred, or 6 or 8 or 2. Don't just look at one half reaction, look at both of them. Okay, so I'm skipping a couple of notes because I tried to streamline that into one slide versus 3. All right, so let's do this problem. So I'm going to do teach something, do a problem, teach something, do a problem. All right, so what's the G cell for this galvanic cell? What does galvanic mean to you? Yeah. Yeah. Give me something related to what we just learned that we need to know. Positive E cell, okay. Positive E cell. So I want this to be a positive E cell. Standard conditions, let's just assume that. So what do I need to figure out from here? Right, which is anode, which is cathode. So you get your little redox sheet out, your reduction potential list. I can tell you them, but it's good for your practice for that. Yeah.
Is this a T-cell sheet for doing the test?
Yeah. I'll give you like anything you ever need. They used to give you a full page of reduction potentials, which was scary. So now what they're doing is they're embedding them in the question. So like in this question, I would actually put the E cell for blah is this and blah is this. So that's why you're in heavy pretty. All right, so what's the E cell for the zinc one? The reduction potential for the zinc. Negative 0.7, 0 point, or point,
0.6.
and copper? Wasn't it like positive 0.337
Yeah.
volts? Okay, who's the anode? Zinc, right? How do you know that's the anode? Because it's negative, it's the lower one. The higher value should be the cathode. Good. So this is going to be the anode. So it's actually written as it should be, anode and cathode. You just have to double check to make sure they're not tripping you up here. So if the E cell has to be positive, that means when you do E of the one that's reduced minus the E of the one that is oxidized, plug your numbers in exactly as you have them. Do not switch around anything. So E cell is equal to red, which was the 0.337 volts, minus a negative 0.763 volts. So you get an E cell as a positive 1.10 volts. All right, so there's E cell. So we got that. We got anode, cathode. So that's what I pretty much here said, who must be oxidized to produce. We just figured that out. So we want to find delta G. What do you want to do next? Maybe what equation comes to mind? Say it again?
Convert joules to work and then find G using the...
You're working too hard. I kind of walked you through that. Go straight to the bottom. Straight to the shapes. NFE? Okay. And negative NFE. So you could do that, but I think it would take longer because we're actually going to be able to do that straight from one equation. Okay, so negative NFE. What is in here? You can visualize this in your head, or you can write out the BCE. How many electrons are transferred?
4.
2. Because if you can actually see it really well. Zinc is being oxidized, right? Loss of electrons.
Yes.
So zinc solid is going to zinc 2, and then this other one is going from copper 2 to copper solid, and so there's an interchange of 2 electrons for each one, right? I may have said that weird. Total is not sum. Total is whatever your number of electrons are in the balance chemical equation. So yeah, if you had to write it out, you'd say zinc solid plus yields zinc 2 plus 2 electrons, and then copper 2 plus 2 electrons yields copper. So overall, you'll see 2 electrons here and 2 electrons here, so it's just 2. Yeah.
What if it wasn't and you had to like multiply?
Do a multiplier, then that you would take what your multiplier was. If this was like 1, for example, down here, and you multiply this whole thing by 2, overall, zinc is delivering 2 electrons to copper, still 2 electrons. So overall, it's 2 electrons. All right, so delta G naught, sorry, I'm really bad with writing naught. That's naught. Delta G naught is equal to negative 2 moles of electrons times the Faraday constant, 96,485 coulombs per mole of electrons, because that's what the F is, times E cell, which is 1.10 volts. Okay? So we're going to eventually be able to cross out our molten electrons. Then we have Coulomb volts. What the heck is a Coulomb volt? A joule, thank you. That's what we previously just talked about in the last slide. So joule is equal to volt. I'm sorry, volt is equal to joule over Coulomb. So Coulomb volt is equal to a joule. Yeah? Okay. So delta G is negative 212.3 kilojoules, because I went ahead and multiplied by 1,000 apparently here. Yeah. Or divided by 1,000. So here we go. What does that tell you about the reaction? It's spontaneous, and it was galvanic, so it was supposed to be, right? You can always like check your values in your math. All right, going on. Cool. Oh, and then this is an example. I randomly have to tell you, sometimes they'll include switches. Switches meaning if you have a completed circuit, you've got your whole anode goes to voltmeter, goes to cathode, and then your salt bridge. Sometimes they'll have an open switch and go, what could you do to fix this battery or cell or something? Close the switch. Make a closed loop. It's really random, but just know that sometimes they have switches that are open, which means this is not connected. Close the switch means it's connected. Like a closed bridge. Huh? Yeah, I think that's closed. Yeah, I just have to tell you the switches. That's why the slide is here.
Okay, I just didn't tell them.
Mission accomplished. That's it. The switch is back. Okay, so let's go through. Oops. Okay, you don't have to write down all of this, but I do want to talk about these things together before we go into the math part. Okay, so we know that standard conditions of electrochemical cells are 1 molar solutions, 25 degrees C, 1 atmosphere. If you ever stray from the standard conditions, that means you no longer can put that not, right? So no E naught, it's just E, or E cell. So you have to consider how is that going to influence everything else? Because you know E cell is like, oh, well, if it's a really high value of E cell, it's going to be really spontaneous. Well, what's really spontaneous? What kind of delta G value? Really negative, like negative 2,000 kilojoules. Not just negative 200 kilojoules, negative 2,000, right? So let's see if we can connect the dots here, and then we'll do the math part for it, okay? So what I'm showing you here is if you change up the standard conditions, your spontaneity could change, your favorability could change. And that's what this is talking about. The spontaneity in the forward direction, by the way. Everything I'm saying so far is kind of forward direction, because we're not talking about reversible reactions exactly right now. So how does it change, you go? I don't know. How does it change? Let's see. If this is what you would say is standard G, which is the not, that's what that symbol stands for, standard conditions, what it's going to change by is this little chunk over here, plus RT ln of Q. What does this mean to you? R should be, just remember this for a second because we're going to talk about it again in a minute. R is dealing with energy. What R value is that? 8.314 joules per mole. Okay, so what is temperature, what must it be measured in? Kelvin. And then this Q thing. What is Q? Reaction quotient, which is blah, blah, blah. Yeah, before equilibrium. Whatever what? Right, concentration of products over concentration of reactants, right? So before you could actually plug any of this stuff in, you would actually need to know the VCE. So you would know, what to include as the products. What do you always exclude? Yeah, pure water and free elements, which would be solid elements, because some of your free elements could be gases, and those are important. Okay. Most of the time, we're going to ignore gases, actually, in this one, because these are all solutions. Electrochemical cells are solutions. They can make gases, but I'll kind of help you out when we get there, because I don't know how much of that you'll see on the AP exam. Okay. So anyway, you have to know the products, because you have to be able to tell me, like, if it's 2, 10, 2 plus, you have to do 10 2 squared. Don't forget that you have to use the coefficients in your expressions. Okay, anyway. So if you want to figure out how much your delta G changes by, you need to figure out is it going to be more or less spontaneous based on the changes that occur. Okay? So what I kind of set up 2 scenarios here. If you want to come up with a new delta G, this is your new value here. You take your negative delta G standard, which is the normal stuff, and let's say you add a really large positive number. How in the world are we getting a really large positive number? Let me go over that part in just a second. how you're getting a really large positive number is that this little expression, your product of those variables, is positive. How is it positive? It's either you have a really high temperature, you're running a hot battery, really, warm batteries, your phone starts to like freak out because it's not very efficient. It's not very spontaneous. It's not wanting to push those electrons to the next place and run things appropriately. So that one we're not as worried about though, because we sometimes will have warmer temperatures and it won't influence our delta G too much anyway. But what's really the problem is we know that reactions occur from, you have reactants and you have products, we got equilibrium. What happens when you have a lot of products in the forward direction? What happens? The forward reaction slows down because it's almost like Le Chatelier's, right? Because if you have too many products, it's like, I've got enough on this side, you guys need to start slowing down and start pushing back to the left. It's almost like the common ion effect. You're going to have less and less and less products made if you already have a lot. So what's literally happening in this battery is if you have too many products there, too many products that are included in the Q value, of course, then the battery's going to stop pushing electrons. If it stops pushing electrons, what's going to happen to the spontaneity of the reaction? It's decreasing. Yeah. What's up? See my sunline? Or you said it's going to lower. Okay. So a really positive value here means it's going to be less spontaneous. And the reason you would have a really large positive number over there is if you have high products. So opposite of that would be why we would have a more spontaneous reaction. So if you're trying to calculate your new delta G, you take your negative galvanic one that you normally have, and let's say you wanted to add, when you calculate, you had a really large negative value. Well, how did you get that negative value? It's because you have really high reactants. Because whenever you take your RT ln of 1 over 1,000, I'm just going to go big here. Assuming this is your reactant, these reactants is going to, whenever you have a larger number in the denominator, it's going to make the ln here a negative value. So this requires a little bit of algebra 2 knowledge of how do logs work, how do natural logs work. So that really negative value means that you're taking a negative value plusing another negative value, so you're getting more negative, right? Which is great. We want to get more negative with delta G, so it's actually more spontaneous. Okay. So more reactants means they're colliding like crazy, colliding with the correct orientation, they're pushing forward, so that's going to mean that your E cell will go up here. As your delta G goes up, it's more spontaneous, right? You're going to have a harder electromotive force pushing those electrons to make more products, right? But on the one we previously talked about, being less spontaneous means that you're going to have a lower E cell because there's just too many products there and it's not going to continue pushing electrons. All right, so we just qualitatively discussed if you have a certain amount of products and reactants, how does that influence delta G and how does that influence E? Because E and delta G are effectively directly related. All right, let's do some calculations with that. I know some of us are very qualitative minds, some of us are quantitative minds. But you will have to explain qualitatively these more than you have to calculate. So I want to make sure we have more practice with this, so don't worry. All right, so now what we just talked about is called the Nernst equation. For the first 2 years of teaching this, I called it the Nernst equation, never realizing there was an N right there. So the Nernst equation. Okay, so this is when you have non-standard conditions present, such as different concentrations than that 1 molar aqueous solution. So I'm going to show you how we get from this Gibbs thing to this thing. And this, I don't know if I have any paper, but I'm going to go with it. All right, so well, you tell me, how do I get from here to here? How do I get from the delta G to the negative NFE? They're interchangeable. I just substituted. Because delta G is equal to negative NFE cell. And so all I did was interchange them. But you'll notice that this delta G is non-standard, which is what I'm trying to calculate. And so I don't put the not there. And then this delta G is standard, so I do put the not here. Because they do mean different things, which kind of sucks. So we have to be very careful. Okay. So then plus the whole RT on the Q thing I was just telling you about, right? Okay, so now let's see, how do I get from here, this funky looking equation, to this one, which is actually the Nernst equation that's a little bit more simplified, okay? So if I want to go from here to here, pretty much I divided by negative NF right here. and divided by negative NF over here. Am I going too fast? Let me give you a minute. Okay. I'll just kind of talk in slow mode. Okay. We're going to divide by this negative NF. Negative NF. Gone. E cells left. Okay. And then over here you got a predicament. You got to do both of these things. Those things that are added together. I don't know what that mathematically is called. Okay, so the negative NF here will cancel. Here will F cancels too, leaving us with just E cell, not E naught cell right here. But over here we've got to kind of consolidate the RT, ln Q, and the negative NF right there together. So that essentially means plus RT over negative NF and ln of Q. So all I did was take that negative and I said minus, and then RT over NF, which is what that is, ln of Q. So that looks real complicated, but there is a mathematical equivalency to that, which I much prefer, and it's called, okay, so hold on, I'll tell you that in a second. It's over there, but you can see it. So I've got E cell is equal to E naught cell minus RT over NF, ln of Q, and Q is, don't forget, it's just products or reactants, whatever your BC says. The replacement for RT F in this whole ln thing, the replacement for RT over F and ln is this. So this is E is equal to E cell is equal to E naught, we're getting those knots again, there we go, E naught cell minus 0.0592 over N log of Q. Now, this used to be on your reference sheet. I don't believe it any longer is. If you needed this on the test, I will give this to you. Because it's not expected that you memorize it. It's expected you know how to do it. How to use it. What these values mean. How you dissect a word problem. Okay? So do not be frightened by this weird looking equation. I got you. Alright? So I just took the E cell, which is this thing over here, is equal to E naught cell minus 0.0592 over N log of Q. So it did change from ln to log. That's why I just tried to make sure you can see the difference. So.
And then I get it. Why did you change my
I don't know. I just
Okay.
wrote what I read. I don't like it, but I like this equation better than any of these other ones. Okay. Because that means that it's already counted for all the constants. I don't know what the conversion between log and ln is, but that's a Ms. Bridger's question. But the R value is accounted for. The T is accounted for because we're not going to change temperature. We're going to change concentration. So this is called the Nernst equation, only changing concentrations, not temperature. Okay. Anything other than 1 molar, you have to use this. Okay. I'm going to scroll down here, and then we'll be done with the new equations, and we'll apply them now, okay? So yesterday we talked about a dead battery, and we said, okay, if this battery has no voltage, that means it is dead. That means it is not going to happen. No electrons are being driven forward, right? And I'm not sure yesterday if I put E or E naught, but if I put E naught, I lied, because that is assuming 1 molar and 1 molar concentrations, right? No. A dead battery has used up a lot of its solution stuff already, its ions, so the concentrations are no longer standard once it started to react. So that's why I want to make sure I didn't, no not there, okay? So dead battery, that means it's at equilibrium, because whatever our reactants were and our products were, no forward reaction or reverse reaction is favored over the other, meaning that we're at equilibrium. So if nothing's favored over one another, the battery's not doing jack nothing. So we have to move on and calculate other stuff from that situation, because that situation is equilibrium. So from that situation, we actually can calculate the equilibrium constant K. So in your equation, we kind of just had, I'm going to plug in the values we just talked about. We just said E cell is 0, and then at equilibrium, you know Q is equal to K. That's nothing new. So nothing new on that one. Okay. So what I just did was I plugged the E in here, because it's 0. I had all this junk over here. I'm just wanted to kind of show you the conversion between those two once again. And originally I had negative RT over NF times ln of Q, but Q in this case is at equilibrium, so it's K. So then I plugged in K right here. and 0 like we previously had. So this is not technically a new equation. It's just you plugged in equilibrium values of 0. So if you ever have to calculate the equilibrium constant of a particular galvanic cell, you can. It's using the Nernst equation and assuming that the E itself is 0 because it's dead. But the E cell, if it were at standard conditions, it's going to be whatever you normally get, the normal way you get E cell, which is E red minus E ox. So anytime you have E naught, you can always look these values up from that reduction potential list, plug it in, and you can actually use your Nernst values here, your BCE to get your moles of electrons, and then solve for solve for K from the log K. And so all of these equations eventually come back to being able to relate to one another. You know, those 4 big concepts. All right, we're going to use these a lot, so just have them in front of you as we kind of go through some problems. Cool. Yeah.
If there's not 298,000,
And I won't, that's not in our curriculum. We only have to do non-standard cells via concentration changes, but in the future when you go to big boy chemistry, then you can use the other one, okay? I just have to show you because I would feel really bad if you got to college, you're like, Miss Ellen never taught me this. So, all right, so let's go ahead and let's qualitatively decide this first, and then we'll do some quantitatives. So if this is your reaction, I've already balanced it for you. Let's just do some chatting first, okay? You can use Le Chat's explanation in anything that does not involve true numbers. Okay, so try this first. What would happen to this E cell? I think we got this was like 1.1 volts when we did this previously on that first two slides ago. So if that E cell is that, or I can just give you any number, what would happen if I increase the copper 2 concentration? Tell me baby steps. Increasing copper 2. What do you normally get to say when you're talking about Le Chat's? Okay, so it's going to shift right. So what's going to happen to E cell? Increase or decrease? Okay, E cell increases because there is an increased driving force in the forward direction. That is it. Do not overthink it. Do not go crazy and like, let me tell you about my life and my future baby mama and like all this kind of stuff. I just want to know it's going to shift right, increase in the driving force of the forward direction. Or you could say increase in the electromotive force if you want to get more fancy. So Le Chat's is very useful. If you had to plug it into the Nernst equation, you could. However, you would need more information than what I gave you so far. I would have to tell you it's increased to like 5 mole or something like that. I have to give you some values there. All right, so then you should know this one. What happens if I increase zinc? If I increase zinc too. Okay. So shift left, decrease the E cell, and then blah 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 blah, decrease in driving force in the forward direction. Okay, we're all talking about forward direction because galvanic cells are always talking about taking whatever we have here and making whatever we have here. So the second example I had was increasing zinc 2+ concentration. All right, so Le Chat's is our friend. You could also throw in there less spontaneous or more spontaneous or thermodynamically favorable. You can use all your big words. No. Okay. And I'm going forward. Okay, this one's a real problem. Okay, mathematics. Math stuff. Okay. Determine the E cell from the previous system, which was, I'll write it up here. Zinc solid plus copper 2 equilibrates to copper plus zinc 2. Okay. Determine the E cell. You'll notice there's no knot there. After the battery is 99.9% discharged, assuming standard conditions initially. So we see after and we see initially. What does that kind of remind you of? Okay, I see it. You can do ice or BDA, right? I'm going to just write BDA here this on my paper, but truly it's an ice table. Because initially, and actually, I know I wrote BDA, because in ice tables, I normally use X's. Thus do you. We're not using X's. We actually literally know how much is changing by. So I'm going to go BDA, okay? So before the reaction occurs, assuming standard conditions, which of these are you actually concerned about? Of all four of these? The ions, thank you. The copper ion, 1 molar, because you can't have 1 molar solid. Like, what does that miss? It's not liquid, right? So, and 1 molar zinc, okay? Assuming standard, ignoring this mess. Okay, so during the reaction, something happens. After the reaction, the battery 99.9% discharges, and you need to determine the new electromotive force. So if 99.9% that discharges, what is left? Which is 0.001, okay? 0.001, you could have, you have a calculator for this. You could take 0.999% of that and figure out how much reacted and subtract, okay? So that means, let's see, we subtracted 0.999 molar. Okay, that's where we're just using that down here. All right, so if you subtract from this side, what are you doing to the other side? Adding. That was a big mistake on our test when we go over some of those. You guys are so flippin' smart, but you didn't add to the other side. So you got a lot of your points except for, based on error, because you continued out beautifully, but you just didn't get the exact right answer. So we'll talk about that. Okay, so molarity and molarity. Okay, so far so good. Next. We got the new concentrations. So you want to solve for E cell. Is there an equation to solve for E cell? Thank you, the Nernst equation. Grace. No, so I don't know what you're talking about. Okay. So Nernst equation. So E naught cell, which we do know it was 1.1 volts, which is from the previous slide, minus 0.0592 over N log of Q. Okay. So before we move on, let's define these variables. This we would if we weren't given it to us. But how would we get E cell? Red minus ox, right? And that would just be whoever red is. Who's red? Who's being reduced? Copper's being reduced because it's going from copper 2 to copper solid, so it's gaining 2 electrons, right? So you could look for the number associated with copper and then the number associated with zinc. Okay, so we could get this, and I already have it for you. It's 1.10 volts. What is N in this problem? 2, because if you look, you can tell there's 2 electrons transferred overall, or you could actually write out half reaction. So that's 2 moles of electrons. And then Q. Q is products over reactants. What is the expression first? Concentration. Zinc ion, zinc 2 plus over copper 2 plus, right? Ignoring both of those solids. Okay, cool. So we can plug in exactly what we have into the log of Q. Okay. So question equals 1.10 volts minus 0.0592 over 2 moles of electrons times log of 1.999 over 0.001. Before you do this, can we take a guess as to if E cell is going to increase or decrease? Why is it going to decrease? Right. Most of the reactants are used up. You got a ton of products. It can't push any more towards products. There's a barrier there going, I can't make any more products. Almost all of them are made. Right. So you know it's going to decrease. Now tell me what it is when you get there.
1.002.
So I'm going to go for 1.00 volts. That's a pretty weak battery. Okay. A little bit of juice left. It actually didn't decrease that much, but that's because the voltages, because we're dealing with like tiny numbers here, okay? All right, cool. So we can do qualitative and quantitative. Yay. What's up?
Is it 1.0 or?
Yeah, it is 1.00. That's what you said, Abby.
Yeah.
Yeah. It doesn't decrease by much, but it does decrease. And you can also explain that with Chatelier's way. All right, cool. So this, oh, I meant to hide some of this. I have more equations for you. Let me walk through this like a teacher. Okay, so we already know this. Check. NEPI. Negative NFE. Okay. If you had to rearrange this, you could go E cell is equal to, divided by NF, negative NF right here. So delta G is over negative NF. What am I getting to here? Oh, I know what I'm getting to. Okay. I forget what I just designed these to streamline stuff here. All right, so if I can rearrange, you good with me so far? Okay, you can see that in this case, I'm so bad, I'm sorry. This is not here. So does this one. Okay. You can see that E cell and Gibbs free energy are directly related in terms of magnitude, not necessarily sign, but magnitude. You know the difference. Magnitude is the size of the number, sign is if it's negative or positive. Okay, so we know this mess. And then separately, we know this mess. We know the Nernst equation. At equilibrium, the E cell by itself, which is 0, you rearranged it from E cell, this one, 0 is equal to E naught cell minus RT over NF. That's a RT, ln of Q, no, okay. So we just bumped this to the other side, so it was negative, negative, positive, positive. Okay, so we know these two things separately. That means that since you've got them both set equal to E naught cell, you can set them equal to one another, yeah? And then you can kind of rearrange some stuff from there. Let's see what we get. Okay, set them equal to one another. So I did E cell equals E naught cell is equal to E naught cell. So this thing is equal to this thing. Not sure what I just did there. So E naught, G naught over negative NFE is equal to blah, 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 blah. Okay? This is eventually showing you that we can solve for K. Okay? Solving for equilibrium, knowing a bunch of stuff. So the last equation of the day is we need to simplify. How can I simplify this, guys? Well, you see it's the same. So this is delta G. It's hard to see the slash right there. Delta G over negative NF equals RT over NF ln of K. What do we do? How? All right, so multiply both sides by a negative NF. Okay, so that means, and negative NF over here as well. So these cancel, and these cancel, leaving me with what? A negative. Okay, so negative da 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 da. So overall, delta G naught, which is that, is equal to negative, because we have a negative RT ln of K. Okay, so our last K we can solve for equilibrium constant K. Okay, so you can know the delta G, and as long as you know information about the temperature and you have a reaction, so you can actually plug in some, well no, you don't have to plug in values, never mind. As long as you know the temperature, you can actually find K, okay? And then this R value though is what? Again, joules per mole K. And don't forget, sometimes G is published as kilojoules. And if that's in joules, you got to do a little metric conversion before you can actually go from there, so from kilos to joules. Okay, cool. So if you know this stuff, how are delta G and K related? If the value of K is really large, what would that be for G? The magnitude is very large, but it's a very negative large number, right? So then delta G is very negative, which is happy because it means it's spontaneous. I wasn't going to write the nose, but it happened. Okay. And then delta G, and when I say very large, I'm like 1 times 10 to the 30th. Okay? 1 times 10 to the 20th. Larger than 1,000. Very forward direction favored. All right, so if the K is small, when I say less than 1, what do I mean? Give me an example. So 1 times 10 to the negative 30th. Never do you have a negative K. Okay? Equilibrium constants have never been negative. You guys would like making up some stuff with that one, but never been negative. Because how are you going to get a negative number when it's just products of reactants? It's just concentration of concentration. So no negatives, okay? So value of K is small, meaning 1 times 10 to the negative 30th, something like that. Then delta G is very small. negative number. So it's just less spontaneous. It's not non-spontaneous, just less spontaneous. Usually. It could be non-spontaneous actually, because your ln could become a positive number. I'm sorry, your ln could become a negative number, which would then offset that previous negative, and we can make it positive. Small negative, or which would leave it very, very low in terms of spontaneity, or non-spontaneous at all. All right, I have more problems to do. Oh, so all that stuff we just talked about connects this big triangle. K, delta G, and E cell. And we just did all that, so we're good here. It's a big happy family. Okay. Yeah, I have to do this, unfortunately. Okay. Unfortunately. So last type of cell, we talked about galvanic cells. Another name for galvanic cells, I didn't actually say out loud. Voltaic, thank you. Galvanic and voltaic cells are the same thing. That was Mr. Volta who came up with galvanic cells, and that was probably in your reading, but I never actually said it. You will normally see galvanic cells. Very rarely will you see voltaic cells. Volta. Okay. Volta also contributed to the volt unit, so now you know about where stuff comes from. Okay, so there's sometimes things where you have the same metals in two different chambers of the cell, and you're like, well, how's this battery going to work if you've got, copper in one and then copper in the other, right? There's no difference in their reduction potential, so you're like fighting to say who's reduced and who's oxidized. But there's actually a way to do it. They're called concentration cells, because you can have the same metal or same aqueous solution of stuff, but their concentrations are different. And if their concentrations are different, then it's not at equilibrium yet. So there is a difference in their potentials, meaning there is a voltage you can acquire. So I would say this bullet, and then what I've kind of written here in green is important. If you get this part, then don't write this part, because it's just the opposite. Like if you can do one, you can do the other. So what happens is if you have two cells, let's say one is 1 molar and the other is 0.1 molar, you have to decide where the electrons flow. I'll give you guys a second to write that actually. Okay, so if you have a concentration cell, you get the same shebang, same stuff in each cell. That means that both of these half reactions are occurring. It's because one of the copper chambers is going to be the anode, meaning it's oxidized, and one of the copper chambers is going to be reduced, meaning it's the cathode, right? So you have half reaction 1 and half reaction 2 happening at the same time in two different chambers. You with me so far? Okay, this obviously, number 1 is written out, oxidized or reduced. It's being oxidized, right? Because you're losing electrons, bye-bye products, right? So what's happening actually in the anode is that you're taking your copper solid and you're making the V on it, right? So you're making more copper ion. What actually controls a cell to make it stop letting electrons flow is when their concentrations become equal, they're no longer different, so they are technically at equilibrium because there's no difference in their concentrations, meaning that no one's going to be losing electrons over the other. So essentially what you have to figure out is who's willing to, which needs to increase in concentration, which chamber. So if I had 1 molar concentration of copper 2 and 0.1 molar concentration of copper 2, the one that's less concentrated is the one that needs to up its ion, right? You need to increase the ion count. So to increase the ion count, the copper solid that's here needs to release ions to solution. And the only way it's allowed to release ions to its solution means it's losing its electrons. Because as the electrons move away, ions themselves are released. So that has to be the anode. So if you need to make more ions in solution, you are the anode. If you have a lower concentration, That means you need to make more ions in your solution, so you are the anode, because the anode is making ion. Therefore, you should be able to figure out who the cathode is. You got 50-50 chance here, right? Okay, so then if you are gaining electrons here, then you are taking your copper too and plating it on your cathode electrode. So you are decreasing, as this is, I'm going to draw my copper up here, as this ion is plated on the copper electrode, what's happening to this concentration? As this ion is plated here, it's going to decrease, and as this ion is made here, it's going to increase, eventually coming out to equilibrium. So that's called a concentration cell. It's sometimes called a Danielle cell. I don't know, but that's what that's just what it's called. So Danielle cells, here we go. Let's do an example. Okay, so concentration cell or Danielle cell. Consider the 0.001 molar nickel sulfate solution in 1 molar nickel sulfate solution. What is the EMF of the system? What am I asking for? E cell. And we know it's E cell and not E naught cell because what's not true? Right, both of them are not 1 molar solutions. Okay. What do you guys want to do first? Chemistry, Google, chemistry. What are you going to do first? Okay, so I'm going to kind of do 2 things. I already know which one's going to be oxidized because we just kind of previously cheated and wrote down that little hint. The one with the blank concentration is the anode, lower. So you already know this is the anode if you can memorize that. But who wants to memorize when you can derive, right? So, here's the anode. Draw the cell. Make a BCE and label who's the anode. And this part is super duper important because in the end, when you have to plug this into the Nernst equation to figure out the new E, you got to figure out who the product is and who the reactant is, right? So, here's the anode. Got it. We know it's nickel. We know it's nickel. We know it's this one right here. Okay. And then we're going to plug it into the Nernst equation. So, let's go ahead and make our little baby cell. We have nickel 2 plus, because that's nickel 2 sulfate, right? I was bad. Oh no. Nickel 2 sulfate. Nickel 2 sulfate. Ugh. Okay, and we know the other one has nickel 2 in it as well. We know both of them have nickel solid, because that's really, we have no choice here. Okay, and then each of these has a half reaction associated with it. What is the half reaction associated? If we're going to call this from the anode chamber and this from the cathode chamber. What is the half reaction with the anode chamber? Nickel solid goes to nickel 2 plus 2 electrons. Okay. And we know the cathode chamber is going to have just the opposite, right? Because it's going to be gaining. So nickel 2 plus 2 electrons yields nickel solid. Okay. The only reason I have you do this is because we have to make a BCE out of these 2 reactions. Right? It's the same reaction though, so you have to write them differently. And then before I move on, what concentration goes in this cell here? 0.0010 molar, and this one's 1.0 molar. Okay, that means the only reason I have you draw it out is because I'm a picture person. This 0.001 goes with this ion that I've created. So this 0.001 molar goes with this product ion. And this 1 molar goes with this reactant ion. And that's important because you need to know who's product and who's reactant. Okay, so when you do combine these 2 reactions, you literally get nickel plus, so that nickel reactant plus this nickel, too many pluses. Oh my gosh, and I keep trying to plug in the 2 for some reason. I keep writing nickel 2 plus as is here. And then that nickel 2 and this nickel solid. So when you write it out like this, you're like, oh my gosh, who's nickel who? I mean, who's which concentration, right? So I like to write it out like this first because then I go, okay, the solid, the product nickel 2 ion is 0.001 molar, and the reactant nickel 2 ion is the 1 molar. Now I'm good to plug into Nernst because I know who the product concentration and who the reactant one is. Yeah.
Why is that the product's concentration?
Because as I wrote out the oil here, we previously said anode oil, right? And we said the anode has to make more ion. Because the anode is going to be the one with the lower concentration.
Okay.
So what has to happen is nickel itself has to lose electrons. As it loses electrons, it's going to deposit out some nickel ion. So I like to write this right next to the anode. So here, this one has to be the anode because it's lower concentration. This one has to be the cathode since it's the higher concentration. Okay, so then plugging into Nernst, we got swept here. E is equal to, what's the E cell, E naught cell in this case? Huh? 0, why? Because it's the same thing. You're doing E red minus E ox, well, they're the same voltages from the reduction potential list. So E cell is equal to 0, which was E naught cell. They were at the same concentration that was, minus 0.0592 over, what's our N? 2, because we have 2 moles of electrons transferred, as we can see from each of our half reactions. There's 2 overall, we're good. And times log of Q. What is Q? Give me the expression first. So nickel 2 plus over nickel 2 plus, right? So that's why you have to know who is who. Yeah, because it's nickel 2 plus, not ignoring that one, right? Over nickel 2 plus. And I accidentally, ooh, did you guys know?
Yeah, I was about to say.
I'm sorry, I just labeled it on the wrong spot right there. Because we know solids can't be molar solutions. Alright, so nickel 2 plus over nickel 2 plus, so basically you just have to do all that as to figure out who goes on top of this fraction. So if you can find a faster way, you let me know. I'm just giving you a fail-safe one. Okay, so that means you plug, plug, plug. I know you're doing it in your head right now. It is 0.088 volts. Positive. Galvanic. Woo! Scored. Okay, one more. Yeah, one more. I like this one. No, it's not long. It's really similar to the previous one that we did with the BDA. It's just about stoichiometry coefficients. It's just an extension of it. Are we done?
Yep, we're done.
Okay. So, determine the E cell. So, E cell means Nernst equation. After when? Determine E cell when. After when E or iron 3 is 0.0050. Okay, so what was it before? 1 molar. Okay, so I'm going to transpose this down here. Zinc plus iron 3 equilibrates to zinc 2 plus iron. Ooh. This is not balanced. How do I know? Yeah, you have 3 electrons transferred on one and 2 on the other, so we have to balance it. Can you do this in your head? You don't have to. I can do it here. I'm going to erase it though, so right click. Not 2 on the zinc.
3 on the zinc, 2 on the iron.
Yeah, it's 3 on the zinc and 2 on the iron, but I'm going to write it out because I already started. So, 2 electrons here, and then iron 3 yields iron, iron 3 plus 3 electrons yields iron solid. So you can see the differences in electrons. That means you just multiply them by their opposites. So this one times 3, and this one times 2. So those coefficients get transferred to those zincs and those irons. So zinc is going to have a 3, iron is going to have a 2, zinc is going to have a 3, and iron is going to have a 2. Cool? Okay, so let's do this whole BDA table here. Starting off with, who do you care about here? Ions only, so 1.0 molar, 1.0 molar, don't care, don't care. All right, who do you know? Or what do you know?
That iron goes to 0.0.
So this is down here after 0.005 molar. How much did it change by? 0.995, okay. So it's almost treated as if it's an LR problem, limiting reagent, okay? You're subtracting everything in between, so this one's 0.995 molar. But as you add to the product side, the products that are made are dependent upon the ratios in which the reactants and products are made, right? Reactant and are produced. So you can make 3 zincs for every 2 irons you use. How do I implement that here? Okay, thank you. 3 to 2 ratio. What am I plugging in there right here? Plus 0.995 and a 3 to 2 ratio. Stoichiometry. 3 to 2 ratio. Remember your LR number coefficient always went on the bottom. Is it coming back? September. Okay, right there. That's where that 2 is. All right, so then that number is 2.4925 molar. E cell is equal to E naught cell minus 0.0592 over N log of Q. Before we plug in, please tell me what these things are. What is E cell? What would you have to do? Who is red? The iron is reduced. Okay. Is iron reduced? Yeah, okay. So this one's rig, and that means this one's oil. So on your paper, you would go looking for the iron and iron 3 combination. Don't just look at iron, because you remember there's iron 2 in there someplace. That one is, I'm just going to kind of write this right here, 0.33 volts. I used a different reduction potentialist, so I only have 2 numbers on mine. So 0.33 volts minus zincs, which is, zincs is oil, which is negative 0.76. So that makes a positive 1.09 voltage. That's our E cell if it were at standard conditions. Okay? So that's E cell at standard. So 1.09 minus 0.0592 over N. What's N here?
6.
Thank you. 6, because the sum or the total exchange of electrons were 6 electrons exchanged. Because previously, you know, I had the 2 half reactions written out. I erased them, sorry. We had to multiply by 3 and 2. So that was 6 moles of electrons. And then log of Q. What's Q made of here? So close.
Zinc.
Thank you. Zinc 2 plus cubed over, thank you. Iron 3 plus squared. That's where people mess up. You go through all this hard work and then you forget to cube and square those based on the BCE's coefficients. Okay, so then the zinc's ion concentration was 2.4925 cubed over 0.005 molar squared. Cool? Okay. Cool. 1.03 volts. Good job, guys. I powered through this. It's from our batteries. Okay. Let's go. Let's see, I got like 25 minutes. If I have to do those 3 sites tomorrow, I can. It's just pushing this back farther. That's cool. Go ahead and start on the Nernst problem set. It's called the Nernst equation in electrolytic cells. AP chemistry practice problems using the Nernst equation in electrolytic cells 1 through 5. You can talk to me about some of these. That's why I wanted to. I didn't know. I didn't look closely enough.
I was sitting right in front of me and I just.
Okay, so try 1 through 5. Ask me questions as you go, and then write down your homework. Electrochemistry FRQs 1996 and 2011. They're on your. It's in your packet. You know where all your FRQs are? In your packet. 1 second. So circle them. I think they're the first 2. Oh, hold on. Maybe I changed my mind. Is 2011 right underneath it?
I don't think there were different problems on mine.
Okay, lies. Do what I had on the homework over there. I didn't notice I had different ones.
1988, 1985.
Are 80, 88, and 85 the first 2?
Yeah.
Okay. That's what I was looking for. I was like, what are the first 2? 80. Alright, so just circle those. Try and talk to me about these. The only reason I'm having you do them in class is because I know you're going to need my help. So, ask around, ask me too.